Hey guys, Struggle here. Welcome to my first proper video. But first of all, Happy New Year. I wish you all the best both personally and professionally. As you saw, the Chinese confetti thingy with plastic cup didn't do anything. And because I cannot be stopped by a simple malfunction, Happy New Year! Okay, I'm gonna be serious now after I clean up my motherboard. What a mess. I have created mayhem over my numerical processor. Jesus. And after I have cleaned up my own mess, guys, I will be talking about the 386 processor in general. And in my case here, there is a AMD 386 DX@33 MHz. But first, let me give you some information about the builds and tests in my channel. I will try to do them as much as historically accurate as possible. That means builds with parts and tests with software and technologies from the proper time period. I will not use modern technologies made to make life without computers easier, because trust me, sometimes old computers can be a real pain in the butt. But despite that, as you probably imagine, I like them. I find them much more interesting than newer ones, and I will also try to make my videos a bit more technical, of course being careful not to make you feel bored. I will also give you some hints I have learned through the years the hard way. So today's example is 386DX from AMD. I wanted to do my x86 videos chronologically, but mine 8086 and 286 are still not ready to unveil their majestic powers. And talking about the beast, the 386 was introduced in October of 1985, while mass manufacturing began on June the next year. It was expensive at first, but became much more affordable after mainstream adoption. The first personal computer to make use of the 386 was designed and manufactured by Compaq, and it was the first time a fundamental component in the IBM PC standard was led by a company other than IBM. It remained in production for 20 years until September of 2007, and I have personally seen it used in embedded systems, telephone PBX systems, and some medical equipment. And an interesting information, it is on board of the International Space Station to this day as well. An interesting remark, guys, Intel introduced in 1988 an SX version of the 386. It is basically a cut-down version with 16-bit databus mainly intended for lower-cost PCs aimed at home, educational, or small business markets, while the 386 now with added DX to distinguish it from the SX version would remain the high-end variant used for workstation and servers. While the SX remained fully 32-bit internally, the 16-bit bus was intended to simplify circuit board layouts and reduce total cost. Performance was, no need to say that, much worse, and it could address up to 16 megabytes of memory. That, however, wasn't the biggest problem because actually machines with 386 are rarely used with more than 8 megabytes of RAM. However, guys, Intel subsequently used the DX suffix to refer to the floating point capability of the 486DX. For example, the 486DX can perform floating point calculation using its onboard hardware assistance, but the 486SX can perform those calculations using software routines. It's much slower that way, no need to say that. But here at 386s, it's different. No matter if you have DX or SX variants, you still need an additional numerical processor to hardware assist those calculations. And those numerical processors, they are different for both SX or DX variants. Now, in my particular case, I have a 386 DX manufactured by AMD, and it's good to know that AMD's 386s, both SX and DX, were almost exact clones of the 386s manufactured by Intel, but legal disputes caused production delays for several years. It's interesting to know that the AMD's 386DX flagship, the 40 megahertz version, which unfortunately I do not own, I have the 33 megahertz one. That processor eventually became very popular with computer enthusiasts because it was a low cost and low power alternative to the 25 megahertz 486 SX. And with that said, guys, I'm now gonna reposition my cameras and show you my components in detail. Now, after I have deployed my IKEA Logitech macro system, by the way, sorry for the shitty white balance, still don't have the right equipment to shoot these videos. We'll see how it goes in the future. Now, the form factor of this motherboard, this is not the original 80 form factor known as Full 80. It was much bigger, and it was introduced by IBM with the IBM AT. Then it was soon followed by clone manufacturers. But by 1985, it was abandoned in favor of the cheaper Baby AT form factor. And this motherboard is using exactly the Baby AT format. It had like a 10 years lifespan, and if you have been for some reason in cryostasis for the last 25 years, you might still consider this high tech. Now it had a size of 330 by 216 millimeters, and it has some problems actually, and I'm gonna show you one of them, especially with P5 motherboards, because of the CPU coolers getting bigger and extension cards getting longer, and you have the situation that your cards cannot fit because they are obstructed by the CPU. And I'm gonna show you this right now. And guys, that's exactly what I'm talking about. As you can see, we have a CPU installed here, and above it we have a heatsink and a fan. And next to it we have this brown slot. It's used to expand your second level cache from 256 kilobytes in our case to 512. And next to it we have those four slots. That's for random access memory 72 pin SIMMs. They can take up both IDO or fast page mode memory. And if we populate all of those slots and our cache module is installed as well, then we can come up to the situation then with all those here populated, they can obstruct installation of long cards on both those four PCI slots and those three ISA slots. And by that time, there were already big cards, big graphics cards, and big sound cards, for example, like Creative AWA 32. And to address the situation, the last 80 form factor, as you can see here, there is no such problem. The CPU is higher and you can install long cards. But by the time this came up, ATX was already taking up the motherboard world by storm, because ATX has some really cool features compared to AT, not to mention the cable management that is much easier with ATXs. Now guys, back to our 386 Baby AT motherboard. I'm going to showcase you some of the elements on it, and then I'm going to turn my macro lens to show you some elements closer. Now I'm going to start with this socket here. It's a standard battery CR2032. It's used for saving CMOS settings and timekeeping. Speaking about timekeeping, that's the time crystal inside, and it's counted by this chip. That's the DMA controller, also real-time clock. Interrupt request, but I'm going to show you this later, and I'm going to also explain how the real-time clock works. This here is quad 2 input AND gate. This here is our keyboard controller, our keyboard connector, 80 standard 80 power connector. Those orange elements are capacitors. as well as those orange one again, but a different shade of orange. We have some inline resistors, those, and some resistors as well here. And here we have, after I told you this is quad 2 input AND gate, those are quad 2 inputs NAND gates. Here we have a clock generator. It's used to create our processor frequency. That's our processor. That's our numerical processor. Here we have 8 chips. SRAM, that's our second level cache. Here we have 64K of it, but it can be configured to up to 256K, and 128K is an option as well. Of course, you need to have the proper chips to populate those slots. 2 more SRAM chips, and those 4 chips here are octo buffer and line drivers with 3-state. I think they are used for memory buffering. And speaking about memory, those 8 white slots here, 30-pin single inline modules, I'm gonna populate them, and I will have a total of 8 megabytes of memory, which is great for a 386. And next to it we have this black ISA slot, but it's ISA only physically. Electrically, it's used to expand our memory. What you do is you install the card on it, and on that card there are some more SIM slots, and you can upgrade your memory to up to 32 megabytes. That's only possible on DX, as I told you, as HIX cannot address more than 16 megabytes. That's it. That's our system BIOS here, and those 2 guys are our main system chipset. This one has a memory controller in it and second level cache controller in it. It also has bus arbitration, clock and reset logic, and the other one has also clock and reset logic, bus arbitration, but most importantly it has the system controller interface. It's connected to this chip here. It has the numerical processor interface. It's connected to our numerical processor, and it also has the CPU interface. It's connected to our CPU here. Here we have 8 ISA slots, 16-bit, 8 megahertz. That gives us a total of 8 megabytes of bandwidth. But as you know, if your card only uses this part, it's 8-bit, and if your card uses both parts, it's 16-bit. And those elements here, we have again some more octo buffer line drivers with 3-state, and those here are bus transceivers. And this single guy here is a hex inverter with mid-trigger inputs. And that's about it. I'm now gonna show you those elements in closer with some more info, and then we're gonna continue. And let's start talking about this chip here made by Chips. That's actually our integrated peripetals controller. It's 100% compatible to IBM PC-AT, and it's fully compatible to Intel's now. This is gonna take a while. There's no other way. So it's fully compatible to Intel's 8237 DMA controller. It's fully compatible to the Intel 8259 interrupt controller, and it's fully compatible to the Intel 8254 timer counter, and it's fully compatible to the Motorola's 146818 real-time clock. And speaking about real-time clock, I told you this is a quartz fork inside a time crystal, and that fork, when subjected to electricity, resonates with 32,768 vibrations per second. That's 32 kilohertz, and there is a logic inside that's counting that, and every time it counts 32,768 vibrations, it counts a second. That's how RTC works, and it's still working that way in modern computers as well. Good to know. And our chip can do some more fascinating things as well. Like, for example, it offers 7 DMA channels for direct memory access. It offers 13 interrupt request channels. It has 114 bytes of CMOS RAM memory, and its DMA clock is programmable. It has an internal divider that can help it work on both 8 or 4 megahertz. That's about all about our chip. We're gonna turn to the star of the show, our main processor. But for your information, I'm gonna attach all white papers for the elements I have found below this video. And in the left corner, the star of the show, working with blazing 33 MHz on 5 volts, draining 1.73 watts of power in 132-pin PQFP package, our star of the show, the AM386 DX-33. And as you have probably noticed, as my teacher said back in the English with Critical Thinking class, Strahil, you have a problem with the TH sound. Now, as you can see here, that's our clock generator. It generates 66 megahertz, and somewhere here there is a divider, and that divider divides this by 2, and that's how we get our processor frequency of 33 megahertz. Now about our numerical processor, it's the Cyrix A7 DOC, and it's in plastic QFP package, but it's mounted on a 68-pin PGA adapter board, so you can connect it to this slot on the motherboard. Another interesting thing about it, as you can see, it says 40QP. This processor has a core to bus ratio of 1. That means that when you pair it with a 33 megahertz central processing unit, as in our case, it will also operate at 33 megahertz. But you can also use this same processor, this same numerical processor, in combination with 40 megahertz 386DX, and it will operate at 40 megahertz. Concerning our main system chipset, you can easily see where the lanes are going. Those are going to the main memory and to the L2 cache. This one has lanes going to the numerical processor, lanes going to the system controller, peripetals controller, and lanes going to the central processing unit. Also has some lanes going to the system BIOS, and the system BIOS is an EEPROM. Under those stickers here, if you peel them, there is a window, and you can erase this EEPROM with ultraviolet light. And now I'm gonna show you how to install your memory. You could start from here, and you install it at an angle, and then after you install it at an angle, you just push it forward and it clicks. But don't do that, because otherwise, if you straighten this up, it will be harder for this one to go inside. So what I do is just like place them all like that. Where's my 4 Samsung memory? There it is. Place them all like that, and when you're ready, you just straighten them, and then you hear a click. After you hear a click, you can move it a little just to be sure that everything's fine, and you do the same with the other slots. Now, what's interesting to know, that's the second shittiest memory connector I know there is. There are worse, but there are also better. And generally, be careful because if you break something here, it's hard to repair, and you know, plastic with time gets more and more breakable. So be careful, no excessive force. If it's not working, there is probably a cause for it. Don't rush it, don't push too hard, and you're gonna be okay. And guys, that concludes my motherboard section, and now I'm gonna talk about the other components. And we're gonna continue with the graphical subsystem. This is a VGA controller made by Quadtel using Trident graphical processor. It's 16-bit full height. Nothing really special about it. It's actually a pretty bad card. Bad because all of the other cards made by ATI, S3 or Cirrus Logic are actually faster. But this one nevertheless has a strong point. It was really cheap and therefore really popular, and that's why I'm using it. The other strong features are you could have up to 1 megabyte of VRAM. Mine has 512K, but by populating those 4 available slots here, you could have up to 1 megabyte. In order for you to achieve that, you need to move this jumper and also play with configuration of this one. So you could have up to 1 megabyte, and for a cheap card like this is a big feature. The other interesting feature is that this jumper here is set to auto detect. It detects the type of the machine you installed the card to, and if it's 16-bit, it uses 16-bit. If it's IBM XT compatible, it will only use 8-bit. So that's a good feature. You could install that card on an IBM XT compatible. If the auto detect function does not work, you could force it by pressing this first switch here to on. And that's why I suppose those two EEPROMs are for the high is for 16-bit operation, the one named low is for 8-bit operation. Something more interesting, I don't know. This here is a clock generator for the graphical processor. This here is a RAM DAC digital to analog converter. Those here are 7400 TTL logic, and we have a standard 15-pin VGA connector. And going from our graphical subsystem straight to our disk subsystem, this is our input-output controller, 16-bit full height. I generally like controllers that have their COM port directly soldered to the board, so I can hook up a mouse without using an additional cable. Next to it we have our printer connector, another COM port here, but this one needs an additional cable, 34-pin floppy disk connector here, 40-pin EDE drive connector, and this is to connect the joystick. Something more, some resistors, some capacitors, more resistor, inline resistors. Those jumpers here are to select the proper IRQ, and a bunch of 7400 logic. This chip here, the Gold Star Prime 2, was manufactured 12th week of 92. And those additional controllers are only used in early computers from IBM XT to the earliest 486s and 286s and 386s, of course. At some point, this functionality will be made directly available on the board, first by using an additional chip, then this functionality will be integrated in this outbridge. And all hail the one and only glorious 170 megabyte monster, the Connor CFA 170. This drive has one disk inside rotating with two surfaces, and therefore at least two head, maybe four, depending on the head type, if it can read or write simultaneously, or don't bother. It has also 64 kilobytes of buffer provided by a Samsung SRAM chip. Its average seat time is around 13 milliseconds, and it rotates with blazing hot to your seats 4011 revolutions per minute. I suppose the 11 is important. I have no idea how they came up with that. It has transfer rates of up to 4 megabytes per second from and to media, and up to 7 megabytes per second to the onboard buffer. And since there is no auto detect in uh, those computers from the era, you need to configure it in system BIOS using all of those system parameters, drive parameters. You need to configure them correctly, otherwise your drive will not be operational, or even worse, you might damage it. And because this is a parallel drive, parallel EDE interface, you need to configure your drive to single if it's a single drive per channel, or master or slave if you're using two drives per channel, or cable select for that matter. You cannot use two masters or two slave per channel. The system will not operate that way. Now we're gonna turn it over and be careful not to stress it. Now, as you can see, there are a couple of ROMs here and here. That's for system firmware, controller, the Samsung SRAM chips, some more controllers, the jumper that configures this drive as master, the connector and the power connector, and something important, where the bolt mounts are here, 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 and here, here, and here. As you can see, the PCB is being cut to make space for the bolt. That said, if you use long bolts, you might damage the board, and if you damage the PCB, you might damage the hard drive, and that's not good for your information. So be careful. And last in today's episode, our floppy drives. We have two of them. One is a Panasonic made 5.25 inch, 1.2 megabyte of capacity, and the other is 3.5 inch NAC made 1.44 megabyte of capacity. We can do it without floppies. We need them to boot the system, install software, copy software, archive software. And basically, I also like floppies, even they break so much. I have no idea why I like them so much. Uh, with that said, guys, I'm gonna end this episode. In my next episode, I am going to build a machine from the parts I have just showcased you. And with that said, if you like my channel, please subscribe. If you like my video, like it. If you don't like it, dislike it. And I wish you a pleasant evening, morning, or a good day. And Computer Caveman out. See you next time.